Let's look at how we can model rotational motion using parametric equations. So our first example, we're going to start with the most basic case. So we're just going to have the unit circle. So I have my x and y axis, and I will have my unit circle. And so we go in motion counterclockwise around this unit circle, and we have the coordinate here 1, 0. So the most basic parametric equation for rotational motion is just going to be our x is equal to cosine of t, and y is equal to sine of t. And this is going to produce our unit circle. Every point corresponds to cosine of some angle t and sine of some angle t. What if we want to go around that unit circle, but say we want to do it backwards? Let's look at case number 2. So we have our y-axis, we have an x-axis, and let's say we want to go around a circle, the unit circle again, and let's say we will do that. But this time, let's say we want to go clockwise. So how can I change the direction of a parametric? Simplest way is simply to change the parameter to be the negative version of itself. So I could take cosine of negative t for x, and I could take y equals sine of negative t. Now that's simple enough to imagine. If you think of t as the angle, if you call this t, well then we're just sweeping out negative angles to start. As we go from like presumably 0 to 2 pi or any other version. Interestingly, this is sort of like a little also, doesn't totally matter. But we could also model this. Cosine is an even function, and so cosine of negative t is equivalent to cosine of t. And sine is an odd function. We could say y is equal to negative sine t. So these would also be a pair of parametric equations that work. But the important understanding is really this. You can just flip the t's to negative t's, and you can change the direction of motion. Okay, so that's great for the unit circle. Then we can do other circles still centered at the origin, non-unit circles. So let's do case 3, and let us do a circle that has radius r. We'll center it at the origin, giving us the point r comma 0. This would be 0 comma r, negative r comma 0, etc. And let's say we're still going counterclockwise, which is how our cosine and sine functions are defined. So all we need to do is multiply our outputs by r. So x equals r cosine t, y is equal to r sine t. And this is consistent with our unit circle definition. R was simply 1, which we don't always write. So what are the radiuses? We multiply it by cosine t and sine t, and gives us the x and y coordinates. Okay. What if I want to go around, let's say I want to model rotate one full rotation every 5 seconds. So let's draw a circle that we want to rotate around, but now we're using our parameter a little bit more. We want that parameter to stand for time, and we want it to actually allow us to know the position after t seconds, and we want it to make a single rotation equal to 5 seconds. So here's my circle. I have r theta, or sorry, r comma 0 is my starting point. It has a radius of r, and we're going to go counterclockwise. So if I want to go around a full rotation in t seconds, or 5 seconds, then I need to go and take the normal period, 2 pi, and divide it by 5. And so that is going to be my, we sometimes call it a b value, but basically what I'm going to write is x equals r cosine of 2 pi over 5 times t, and y is equal to r sine of 2 pi over 5 times t. And so we can see if I plug in 5 for t, let's say x equals r cosine 2 pi over 5 times 5 going in for t, the 5's cancel, and I get x equals r cosine of 2 pi, well, just 2 pi. And so that represents the x-coordinate right here, one full rotation, and it occurred when t equals 5. I make it all the way around. Similarly, I could say y equals r sine of 2 pi over 5 times 5, cancels, so we get sine of 2 pi. And I can get the coordinates at any time t. So t is now being input and it represents the number of seconds. Multiplying it by this 2 pi over 5 means we're going to travel as far along as we should on this circle, such that it would take 5 seconds to make it all the way around. So that's how we can use time as a parameter and model a rotation over a certain number of seconds, minutes, whatever we want our parameter to be. Okay, let's look at a case where we don't have a perfect circle. So let's do, and we're going to center at the origin again. And let's say we have a starting coordinate of 3, 0, and a y-axis coordinate of 2, 0, and then we'll come around and we'll get to negative 3, 0. And then down here we'll come to negative, 3, 0, 0, 2, 0, comma, negative 2. So what we should have here is more of an ellipse than a circle. So we'll go around and it's sort of like the circle's been stretched out a little bit. Here's my ellipse. Let's see if we can get this to fit. Not exactly. There we go. Okay, so this makes an ellipse. And so compared to the unit circle, which would just be sitting here, right, which is, remember the unit circle is x equals, well, just cosine t, and y equals sine t. Compared to that, my ellipse, my x has been stretched by 3, multiplied by 3. So I can say for my ellipse, x equals 3 cosine of t. And I can say that y has been stretched by, or multiplied by 2, so y is equal to 2 sine t. And so this is my parametric equation to model the ellipse. I can get my stretch in the x by stretching the x, the stretch in the y by stretching the y. And so I get the equation of the ellipse. Let's say I want to go around this ellipse. Let's say I want to go around the ellipse once every 10 seconds. Okay, every 10 seconds. Or let's do a different unit. Let's say minutes. I do 1 full rotation. Well, that means that when t is 10, I want to be inputting 2 pi. So to accomplish that, I need to take 2 pi, divide it by 10, which is equivalent to pi over 5. So if I want this to be true, that I rotate around once every 10 minutes, I could use x equals 3 cosine of pi over 5 times t. And I can say y is equal to 3 sine pi over 5 times t. Notice how when I plug in 10 for t, the inside will become 2 pi, and that's when 1 full rotation has occurred. If I plugged in 5 for t, the inside would become just pi, so I would make it halfway around in 5 minutes, and I can plug in any t I want and know where I am around the circle at that time t. So if I want every 10 minutes to be 1 rotation, I can use this b value to accomplish that. Okay. The other thing I could do is I could change my starting position. So if I wanted to start like here, and let's say that corresponds to the angle, let's pretend that's pi over 6. Right? If I wanted to start there instead of starting at 3, 0, well, it's actually very easy. I can just add pi over 6 inside my function. The easiest way to think about, well, why does that work, is because now at time 0, if I plug in 0 for t, these both become 0, and I am taking cosine of pi over 6 and sine of pi over 6. Has that been the 3 the whole time? Oops. So 3 cosine pi over 6, 2 sine of pi over 6, and that's going to give me this exact coordinate here. So the parameter time when t equals 0, my trig functions take this angle and produce this coordinate here. So I can also set off and not just start it here. By default, all the trig functions assume you're starting here, but you can offset that with these things. All right, what was that? Case number 5, I guess? This was 5. Case 6 we're going to look at is what if our rotation is not on the origin or centered at the origin? So for this case, let's say I have some arbitrary point A comma B, and that my object is rotating, and let's just say it's a circle for now with radius r around A comma B. And let's say it's counterclockwise. So what we can do here is just compare to the unit circle. So if I have the unit circle here, or let's say this is some other circle with radius r, basically all I have to do to get this circle onto the green circle is just translate it. So I need to translate the center to the center, and then every point on the circumference of the circle is going to translate to the corresponding point on the circumference of the new circle. So every point is going to go to its new location. So it's just a basic translation. Translate by x turns into x plus a, y turns into y plus b. What does this mean for a parametric equation? Well, it's very easy. Let's say that x is equal to r cos theta, and then after that we just add on a plus a. So say we were here, r cos theta would give us r comma 0, and then if we add a, that brings us in the correct direction by a units. And so adding a is like adding a, right, plus a. Similarly, y is going to equal to r sine theta, and then we're just going to add on b. We're also going to turn and go up. And in doing so, we land on our proper coordinate. So generally speaking, if I want to center my rotation at some point a comma b, I just take my curve, and then I just can add a and add b. Now my favorite thing about this is you can stack this and you can create double orbits and triple orbits. And so what I mean by that is, say we have the sun, for example, and let's put the sun at the center of our coordinate system. So here's the sun. And let's say we have the earth, and the earth is rotating about the sun, right? So round and round we go. And so the position of the earth, well, pretend that's centered properly. You're just gonna have to pretend. Or maybe I can move this. All right, so let's say the Earth's going around, and let's say the radius from the Earth to the sun is r. So we can say the position of the Earth is given by x is equal to r cosine of, and let's say we go around the sun every 365 days. And so let's let t be days. And so we go 2 pi in 365 days. So I'm going to say r cosine 2 pi over 365 t. Right? And then y is going to be r times sine of 2 pi over 365 t. And so this is going to model the path of the Earth. But guess what? The Earth also has the moon. So let's do the moon here. And around the Earth goes the moon. And so the moon, let's say it goes around every 28 days. So we can take 2 pi over 28, which simplifies to pi over 14. So that's going to be my period. Well, I don't know if that's the period, but that's our b value. But what I'm trying to say here is we're centering that rotation at the Earth. So all I have to do is take the Earth and add to it the rotation of the moon. So let's say the moon is m units from the Earth and it's going in a circular orbit. Well, then the moon's rotation can be modeled by x is equal to, the moon is m cosine of pi over 14t. The x or the y coordinate is m sine of pi over 14t. This by itself models the rotation around a fixed body, but since we're in this xy plane and the Earth itself is already moving around and round, we're just going to add wherever the Earth is, right? This is basically like our A and our B from here. But our A and our B are just consistently changing. But that's okay, we can let things change because it'll always be in the correct spot at time t. So all I need to do is add from here our cosine of 2 pi over 365t. And here I need to add our sine of 2 pi over 365t. And this is going to model the path of the moon. And now it is kind of depends what the curve is going to look like based on the speed of the moon relative to the speed of the Earth. And I'd kind of like to look at what this looks like.